Hello, my name is John,
And my name's Aniket.
and we researched the process of creating artificial snow and how you can create your own snow making system at home.
First, we're going to go over the science, then we're going to go over the pressure washer, then the air compressor, then the mixing chamber, the requirements, and the process. So, some basic discovery is the first artificial snow was created in the 1940s by accident when scientists at a Canadian military research facility were testing water spray systems in cold conditions. The first commercial snowmaking system was developed in 1950 by a group of engineers experimenting with pressurized water and air. And lastly, by the 1970s, snowmaking became a crucial part of ski resort operations. And then let's go into some history. Artificial snow revolutionized the ski industry, making it less dependent on natural snowfall. The Winter Olympics rely heavily on artificial snow for consistent conditions, as seen in Sochi 2014 and Beijing 2022. Artificial snow extends ski seasons, generating billions of dollars annually in tourism revenue.
The process of making artificial snow is a simple but specific process. Here's a general overview of the tools needed in the process of making snow. So first you have water from a pressure washer, which is pumped into a chamber. And then you have compressed air, which is also injected into the chamber where it mixes with the water. And then water-air mixture is cooled and broken into tiny droplets by the nozzles. And then the droplets freeze into ice crystals as they are released from the chamber and set into the cold air.
First, let's learn about the pressure washer. The pressure washer is a key component in making artificial snow. The pressure washer pumps water at high pressure into the snowmaking system to ensure it flows forcefully through the nozzles and aids atomization. We used the Ryobi pressure washer that provided 1.2 gallons per minute at 1800 psi of water for our snowmaking setup. The 1.2 gallons per minute of water provided just enough water flow into the chamber at a maximum pressure of 1800 psi. Water is pumped into the snowmaking system at very high pressures, typically ranging from 400 to 800 psi. High pressure ensures that water is delivered in a steady, strong stream to the nozzles. It provides the energy needed to break the water into small droplets when mixed with compressed air. The pressurized water is then forced through specially designed nozzles. These nozzles have very small openings, which help atomize, also meaning break apart the water into tiny droplets. High pressure water creates very fine droplets, which are essential for quick freezing. As the droplets mix with the cold outdoor air, they lose heat rapidly due to their small size and high surface area to volume ratio. This rapid cooling causes the water to freeze into solid ice particles before hitting the ground.
Next up, we have the air compressor. The air compressor supplies high pressure air to the mixing chamber and cools the water while breaking it into tiny droplets. We used the McGraw air compressor that provided 4.1 cubic feet per minute of air at 150 psi for our snowmaking setup. The 4.1 cubic feet per minute of air provided enough airflow into the chamber at a pressure of 90 psi when actually released from the tank. Next, let's go over some details about the air compressor. So the compressed air is stored in tanks or generated by an air compressor at a high pressure, typically around 100 to 200 psi. When it's released into the mixing system, the air expands rapidly. The rapid expansion causes a drop in air pressure, which then drops the temperature. The expanded air can cool by 10 to 20 degrees Celsius, depending on the initial compression pressure. This is known as adiabatic cooling, where energy in the air is used to expand the volume rather than increase its temperature. I'll go more over that on the next slides. This cooled air lowers the temperature inside the mixing chamber and around the water droplets, helping them freeze faster when sprayed into the cold outdoor air. Compressed air flows into the chamber where it mixes with pressurized water. The force and speed of the air creates turbulence, which then breaks apart the water and forms tiny droplets. Smaller droplets have a higher surface area compared to their volume, which allows them to lose heat to the surrounding cold air more quickly.
As John previously introduced, adiabatic cooling is a process where a gas, such as air, cools as it expands without exchanging heat with its surroundings. This happens because the energy used for expansion reduces the temperature of the gas. Some applications snowmaking. In artificial snowmaking, compressed air rapidly expands when released, causing a drop in temperature. This helps cool water droplets quickly, increasing the chance of them freezing before reaching the ground. And a natural occurrence is that adiabatic cooling is a natural phenomenon, seen in weather patterns as warm, moist air rises in the temperature. It expands due to lower pressure at higher altitudes, causing it to cool and form clouds. And then let's go into the mixing chamber. The mixing chamber is the last tool needed And the mixing chamber combines high pressure water and compressed air in a controlled environment to ensure that water is atomized and pre-cooled before being sprayed through the nozzles. So just some detail about the mixing chamber. The mixing chamber is a critical component in snowmaking systems, where compressed air and pressurized water come together. It controls how these two elements interact to create the fine mist needed for artificial snow. It ensures the air and water are mixed uniformly for considerate droplet size. Allows the compressed air to cool the water droplets before they're ejected from the nozzles. As compressed air enters the chamber, it expands rapidly, cooling down. Water enters the chamber under high pressure, typically between 400 to 800 psi, as previously mentioned. The force of the air disrupts the water stream, reducing it to a mist of fine droplets. The cooled compressed air absorbs some heat from the water droplets, further lowering their temperature. This pre-cooling helps the droplets freeze faster once they are exposed to the cold outdoor air.
So here's the actual mixing chamber that we created. It features a place where you can connect your pressure washer and then the air compressor down here. And there is a ball valve right in between that allows you to control how much compressed air is mixed into this system, which affects how efficient it creates the actual snow mixture. And you use two smaller size nozzles at the top and one larger one at the bottom, which acts as a nucleator for the more higher percentage of water mixture to freeze on top of the more compressed air mixture. And all this must be done under the right conditions to create snow. And then I also chose 1/4 inch pieces to allow for more external mixing rather than internal mixing. Next, let's get to the specifics of how ice is actually formed. Ice is a result of a liquid becoming a solid by an event called nucleation. A water must first reach its nucleation temperature to freeze. There are two types of nucleation. The first is called homogeneous nucleation, which occurs in pure water with no contact with any foreign substance or surface. With this type of nucleation, the conversion of temperature occurs by changes in pressure or primarily temperature. In a homogeneous nucleation, the nucleation begins when very small volume of water molecules reaches the solid state. This small volume acts as an embryo and becomes the basis for further growth until all the water is converted. Molecules are attaching and detaching from the embryo at rapid, equal, and very quick paces. As more molecules attach to the embryo, energy is released, causing the temperature of the attached molecule to be lower than the temperature of the attached molecules. The growth rate continues until all the molecules are attached. At this point, you have the solid state, which is ice. Next, let's go over what heterogeneous nucleation is. The heterogeneous nucleation process is when ice forms at a temperature at higher temperatures than what is needed in homogeneous nucleation. This is due to the presence of foreign material on the water. This foreign material acts as the embryo and grows more rapidly than embryos of pure water. The location on which an ice embryo is formed is called on-ice nucleating site. As with homogeneous nucleation, heterogeneous nucleation is governed by two major factors: the free energy change involved in forming the embryo and the dynamic of the fluctuating embryo growth. In heterogeneous nucleation, the configuration and energy of interaction at the nucleating site become the dominating influence in the conversion of water to ice. Snowmaking involves the process of heterogeneous nucleation. Next, we have this more getting into more details of what heterogeneous nucleation is. So there are many materials and substances which act as nucleates, such as snowmax. Snowmax is a low temperature nucleator that is found in large numbers of untreated snowmaking water. The nucleation temperature of snowmaking water is between 15 degrees Fahrenheit and 20 degrees Fahrenheit. As water droplet size cools, heat energy is released into the atmosphere at the rate 1 calorie per gram of water. As it freezes into an ice crystal, the water droplet will release additional energy. This quick release of energy raises the water droplet temperature to 32 degrees Fahrenheit, where it will remain. Freezing continues. This is the one reason why we are accustomed to thinking that water freezes at 32 degrees Fahrenheit. To be precise, the water will continue to freeze as long as it remains or below 32 degrees Fahrenheit, but only after it has reached its nucleation temperature. Any excess energy will be dissipated into the atmosphere.
What is snowmax? As John mentioned snowmax before, many ski resorts use snowmax in their snowmaking machine. Unfortunately, we were not able to get hands on snowmax. But what exactly is snowmax? Snowmax is a snow nucleation additive made from freeze-dried Pseudomonas syringae bacteria, which enhances the formation of artificial snow. Snow forms when water droplets freeze around a solid surface in nucleation. SNOMAX contains proteins from Pseudomonas syringae, which provides the ideal surface for ice crystal formation. Normally, pure water supercools below 0 Celsius before freezing. SNOMAX triggers ice formation at higher temperatures, around -3 Celsius to around -5 Celsius, due to Pseudomonas syringae bacteria, containing an ice nucleating protein that mimics natural ice formation. These proteins arrange water molecules into an ice-like structure. This speeds up the crystallization, producing more uniform and powdery snow compared to regular artificial snow. So let's go into Pseudomonas syringae more in detail. Pseudomonas syringae is a gram-negative bacterium found on plants, in soil, and in water. It is known for its ability to act as an ice nucleating agent, meaning it can help water freeze at higher temperatures than usual. Ice nucleating protein, INP, contains specialized proteins that organize water molecules into a crystalline structure, encouraging ice formation. How it works? Well, Pseudomonas syringae is freeze-dried and used in snowmaking machines like SNOMAX. When added to a snow gun system, the ice nucleating proteins encourage water droplets to freeze at temperatures as high as -3 Celsius to -5, previously mentioned, rather than -8 Celsius or lower.
In order for artificial snow to be formed successfully, there are specific requirements that must be met. Oftentimes, the snow created is icy or watery slush, which occurs when a requirement is not met. So first, let's talk about the pressure. So without sufficient pressure, the water will come out in a weak stream, which means there wouldn't be enough pressure to create atomization of the water. And also with compressed air, if there's not enough flow of the air, it won't be able to shatter the water into small droplets. Next, the temperature plays a crucial aspect in creating snow. For the droplet to freeze, the surrounding air must be below freezing, typically a wet bulb temperature at 28 degrees Fahrenheit. Humidity also plays a huge role in making snow. The humidity of the air dictates whether snow will be formed or not, regardless of the temperature. When humidity is low, water droplets lose heat faster through evaporation, making it easier for them to freeze. Lower humidity allows water droplets to supercool more efficiently before forming ice crystals. In high humidity, evaporation slows down, reducing cooling efficiency and leading to the water becoming wetter and slushier snow. High humidity can cause droplets to remain in liquid form longer, which delays nucleation. So next, we have a chart displaying the temperatures and wet bulb temperatures. So if you look here, you can make snow at 32 degrees Fahrenheit as long as the humidity is at 20%. But once it goes to 80%, you can't make snow anymore as the wet bulb temperature becomes too high. Same thing with at lower temperatures. Even at 28 degrees Fahrenheit at 70% humidity, it's hard to make snow.
So before we end our presentation, I just want to go over some fun facts. First of all, some ski resorts use treated wastewater for snowmaking to conserve fresh water. And next, the energy cost of snowmaking is significant. Resorts can spend over $500,000 per season on snow production. And lastly, there's an ongoing debate about the environmental impact of artificial snow on local ecosystems. And here are the sources we use for our presentation. Thank you for listening.